Hey y'all, gonna do example 1614 in the book. We have a disk that rolls without slipping, and it wants us to find the acceleration of point A, the contact point on the ground. They give us its omega, or angular velocity, 6 radians per second, and its angular acceleration of 4 radians per second. Why would this point have an acceleration? Well, as this rolls over, this point is going to be lifting up, and it's going to be maybe moving over to the right. Right? If you just think about, it could have some normal and tangential component. How about that? So the first thing I'm going to do, so we can use our relative acceleration equation, is to find out what the acceleration of g is. And we can do that. Oh, the acceleration of g is just going to be equal to alpha r. And we know alpha, we know r, so 4 radians per second squared times 0.5 feet. And we get 2 meters or feet per second squared. And that is going to be in the I direction. And we did this with scalar analysis, so we need to give it a minus sign to show that it's moving to the left. Alright, now we can say, what is the motion of this point A with respect to G? The acceleration of A is equal to the acceleration of point G, which we just found, plus alpha crossed into r. And the r we want right now is r of A with respect to G. Okay, and we have a minus omega squared in the direction of r. Okay, we have everything on the right hand side now. We know that this is a negative 2I for the acceleration of g. For alpha crossed r, that's going to be a 4k. It's the counterclockwise or positive k direction for alpha, crossed into a negative 0.5 j. That's my r of A with respect to g. Just goes down 0.5 feet. Alright, and then we have omega squared. Omega was given to us, and in the direction of r, which is 0.5 minus 0.5 j. Okay, we can take the cross products. I get a negative 2i. This one will give you a positive 2i. Those go away. And we're left with an 18j. So the acceleration of the point at the bottom is just going up. At the next instance, as it rolls, and we look at the point here, it's going to have some acceleration that's up and to the right, and I'd have to calculate further around the circle to give you a good description. But there we go. As we rotate that point that we call an instantaneous center, we find out cannot be used to find accelerations. It's an instantaneous center of zero velocity, not an instantaneous center of acceleration. I don't know of a method to find those. But for velocities, you could use this. Alright, thank you.